recording. All right, guys. So hello, everybody. And so we want to start today. Kind of focus a bit on some things. Let's look at TIG welding. So let's say like set up how we get this whole thing rolling here. So first and foremost, before we do anything, is cleanliness is really kind of the #1 issue here. So one of the things we want to do is, not just clean your metal, but a really important one is you want to clean your workspace. You want to make sure that your actual surface you're working on is not contaminated by something. This is acetone. So in terms of what you clean, so you can see right there, this will get in the weld. So we want to clean this stuff off. So in terms of cleaners, acetone is the first one of choice because it doesn't leave any residue. Acetone completely evaporates, leaving no oil, no residue whatsoever. Now, second, you say, oh, why can't they use alcohol? Remember, alcohol is only like about 30% actual alcohol. The rest is water. So even if you wipe down with alcohol, you're still leaving water residue behind, which can cause issues. So really the one you want to use is acetone. And of course, the acetone being what it is, this is now highly flammable and extremely dangerous. So when you're working with this stuff, be mindful where you're tossing this rag. And right now, we'll all be dizzy and really like sick in a few minutes if we don't get rid of this thing. But also, anywhere around, if you have like any kind of heat source, even a window with sunlight coming through, can ignite this. All right, really strong sunlight focused through a window pane can ignite this rag, and it's happened in a friend of mine's shop. So you want to be very careful with it. So you want to make sure our workspace is clean. Another one is we really want to make sure that the wire itself is also clean. Let's see, this is not a clean spot on here. If you watch on here, even the wire is going to be giving off some material as well. So even if you take it right out of the container, here's a piece of stainless out here, even right out of the container, it's going to have oil on it from the manufacturing process. The wire is drawn, which is drawn through dies to basically stretch, a bar down to this size through metal dies, smaller and smaller holes. They use a lot of oil to do that. They don't clean it off. So when you get the wire in this container, don't assume it's clean. So you can see right there, this will get into your weld, and especially stainless aluminum. If you see that black crud floating on your weld pool, a lot of times that's where it's from. You may have cleaned the metal, but did you clean your wire? Did you clean your work surface? All these things are potential contaminants that you really have to be aware of. Another one is this, which you see says aluminum only. So this is a stainless steel brush. This is aluminum only. You want to make sure that you have got a dedicated wire brush. I have a piece of Scotch-Brite right here. This is brand new, never been used for anything. So you don't want to just grab any materials off the table or around it, even if it's brand new. If this has been sitting and it's got like grinder dust that's just been dropping through the air onto it and settling onto it, you may not see it, but when you go to clean your aluminum or your stainless, you're going to be driving those steel particles into the surface, and you'll never know it until it rains. And so it's very important that you want to make sure that all the stuff you're working with is as clean as possible. So whenever you're working aluminum or stainless, you have brand new out of the box Scotch-Brite, brand new out of the box grinding wheels or flap wheels, or brushes. If you have any question like, well, I don't know where that's been, don't touch it. So you want to maintain these things. It's a very important consideration when you're working on it. That's why aluminum is such a pain in the butt sometimes, because you have to be really careful about these things. So let's look at aluminum, because I think that's going to be a fun part here. So I have a piece right here. So taking this rag right here, let's see what's going on. So I'm going to use a little more. Forgive me, I know this really smells, but We gotta do what we gotta do.
Acetone, then brush or brush, then acetone?
Yeah, so you want to first acetone first. So watch what happens. So first I'm gonna hit with acetone. This, well, same stuff.
Can you use brake cleaner?
No. Brake cleaner has other things in it, which I don't know what they are. Primarily because acetone, we know what this does. Brake cleaner has other chemicals in it. And one of the things to be aware of is, let's say this is an engine component or something, machine component. Maybe there could be other parts attached to it, O-rings or something, seals, whatever. Brake cleaner can attack a lot of plastics and stuff in the worst way. It's very aggressive. So we want to stay away from those things. Acetone, we know what this stuff is. This is dead clean. It won't attack anything. It's actually quite safe for a lot of types of rubbers and O-rings. It will not damage them. Alcohol actually will, by the way. Like alcohol used like for just medical stuff actually attacks a lot of rubber O-rings that are used for engines and machines and stuff. So yes, yeah, you have. Yeah, that's one thing that you'll learn if you go into that kind of industry. Rubbers fall into the rubber seals, washers, O-rings fall into two camps. There'll be ones that are like, there are ones that are alcohol proof and ones that are like acetone proof. It's very complicated, but it's an interesting thing. It's like you have to use the right kind of rubber seals depending on what's going into those pipes or whatever else. It's not like one size fits all. It's like a whole other like can of worms you have to open up. This can actually come into play. Anybody who works in engines or something, you'll know what I'm talking about. Yeah, it's like there are things that are gasoline proof. Yeah, it's like you have things that are gasoline proof, but then like ethanol, alcohol will dissolve them like overnight, which is one of the reasons why ethanol filled gasoline that we have in our cars and stuff out here now is such a nightmare. It attacks a lot of components in the engines that are just, it's really horrible stuff. But for industrial machines, you run into that same issue. There's some that are like fuel proof, oil proof, but they're not alcohol proof. And the ones that are alcohol proof, but they're not gas proof or oil proof. So it's two camps that don't quite intermix. It's complicated and interesting. So here's what came off of it. So this is, just quickly you can see, this is the dirt and grime that's on the surface. I'm gonna turn it over, do the other side over here. Again, the aluminum is brightening up quite a bit. So this is just surface grime. Now I'm going in the same direction as the grain, okay? The metal has a grain to it and I want to keep going on that same grain. Get as much off as I can. Now if you're being really careful, you do this till it comes off almost white. But yeah, that's pretty good. So now I'm going to take this and I'm going to rub the surface and clean off what I can't get off with the acetone, which is on here you do have a layer of aluminum oxide on the surface. So remember, the aluminum oxide is formed through the interaction with the air. You can't see it, but it's there. And the aluminum oxide is exactly the same as what's in this right here. This is the same stuff that's on here. So you have a layer on here, it's invisible, you can't see it, but it's there. And it's just as hard as sandpaper is, just as abrasive. So you need to remove this before welding. You got to get that off of there because the aluminum oxide melts at a much higher temperature. So right now you've got this basically heat-proof shell on the surface of aluminum. That's what makes aluminum so nice. It doesn't rust, you know? It doesn't rust. That's why we like this stuff. But at the same time, if you're going to weld it, you got to remove it. So we want to abrade it away. Hopefully you'll see the aluminum change color a little bit. It'll change. You see that? It's getting brighter. I'm removing the aluminum oxide layer right now by abrading it. I like Scotch-Brite because it's fairly gentle. If you use sandpaper, you can risk getting the crystals of this stuff jammed into the aluminum. Now you've got little rocks in the weld and it's a real pain. So Scotch-Brite is really nice in that respect. So I'm gonna rub it all over, going with the grain. And I want to remove that layer off the surface. That looks pretty good. So you can see right there, here's some of it here. Now take some more acetone. There we go. Look at that. Yeah, so that's the aluminum oxide layer that I've removed. So now it's naked. It does not have the protective layer on here anymore. Downside is you've got 20 minutes to work on this thing. Within 20 minutes, that layer starts to react with oxygen and starts to protect itself again. So let's say you clean it off and you're like, oh, I gotta go to lunch. You come back and you're like, well, what should I do? Clean it again. The same is true with aluminum, with stainless steel. So once you've got the cleaning protocol done, and and if you take a break or something, you gotta repeat it again. You gotta go back and lightly abrade it, clean it again to remove the oxide that's been deposited. Let's say Friday, you come back Monday morning, you have to repeat that procedure again. So it's something you want to be mindful of. So now it's clean, we're ready to go. All right. So let's get some aluminum wire out. We got in the bin here. I think this is mostly stainless. Can you get me a couple of pieces of aluminum, the larger diameter, please, the biggest one? So while we're waiting, so this is the rod that was sitting on the shelf on the booth over there. So you want to make sure you don't do this. You notice this one has been melted on this side. It's been burned off on this side. You want to make sure when you're working with the wire, only melt one end, okay? Keep the designation, the printing on one side of the wire, because if you have wire laying around and you don't know what it is, it's junk metal. Now it is mystery metal. You don't know what it is. Very important, only aluminum wire. Aluminum, that's steel. So you want to make sure you keep this on there. Everybody got that? This is really important, because if you're using very expensive wire, 316 is not cheap. Or if you're using another like titanium wire or something else, it's extremely expensive. So you want to know what it is. Thank you very much. So always make sure you leave that designation on the wire so that you can read it. So what do we got here? So this wire on here, this one is 308. Now, if you're welding stainless steel, all right, I'm sure you've used 316 here, right? Okay, so here's some new information. The number on here, this is a very important thing to keep in mind. When welding stainless steel, you want to use the correct alloy for what you're doing, because yeah, 316 may work, but if it's going to be tested and analyzed, the alloy's got to be correct. I mean, I did this for a very, very long time in industry. And you want to make sure you use the right alloy for the right purpose. This can have impact, not about strength, okay? But the impact is when it's exposed to corrosive liquids. It's exposed to salt, to acids of some sort. Remember, the heat effector zone is where it's going to eat away first. If the weld is the wrong alloy, that weld is going to dissolve, it's going to get eaten away very quickly. So the proper alloy is important here when you're doing this stuff. It's not so much about strength, it's about corrosion resistance. So what is 316 used for? It's used for 316, okay? This metal right here, ordinary stainless, is 304. The same alloy used in, like, say, your kitchen pots at home is 304. It's like the standard, most commonly used stainless steel is 304. You weld it using 308, okay? 308 is the correct alloy to use for welding 304. Now, another case is like the thing you were welding, which is stainless steel to mild steel. In that case, the proper alloy is one called 309. Okay, 309 is what you use to weld stainless to mild steel. Why do we do that? Now, if you remember back to weld principles, when you weld two metals together, okay, let's say this let's weld this to the table, okay? The two metals intermix, correct? They combine. One of the things that happens is the intermix is Remember, it's also being heated. Remember, you start losing some of that carbon, you start losing some of that chrome that makes it hard. So 308 has extra amounts of chrome in there. It's got extra amounts of carbon in there, so that as it's welded, it actually has a little extra to compensate for heating and blending into the mild steel. So the weld doesn't lose its strength, nor does it lose its corrosion resistance. That's why it's done. So these are things that you'll learn depending on industry you go into, but it's a good thing to remember. We want to use the right alloy for the right purpose. It's not always about strength. Yeah, 316 will weld it on there, but in the application, that's where it's critical. We use stainless not because it's strong. We use it because it's corrosion resistant, right? Because it's expensive. If it's strength, I could just use mild steel. It's a lot cheaper. I use this because I need something that's not going to rust, that's acid proof, that's going to be resistant to salt water, high temperatures, you know, you name it. So it's all about corrosion resistance, all right? That's really the key here. I don't know if I have any 309 in here. We didn't use a whole lot of it back in the other shop, but that would be the correct alloy. So let's look at aluminum. All right, so I got my aluminum rods here. Again, just like before, I want to wipe these down, and I want to get off any potential corrosion that's on the surface. And see, there's a little bit, not too bad, there's a little bit on there. Now, people who are really finicky will even take this and actually wipe down their wire with Scotch-Brite just to be dead, because remember, this is going to have that layer on the surface too, okay? Thinner, but it's there. So some people actually do that. These are all the things you might want to look at. Like if you're welding and you see, oh wow, where am I getting what they call the salt and pepper on the surface? These are things to look for. Where is this corrosion coming from? Yeah, so some people even wipe it down with Scotch-Brite, then alcohol, just like they're prepping the base metal. Same thing. But we don't do that today. We'll just wipe it down with acetone and live with it. So now let's look at the tools. So we have our TIG torch here, and let's see what we got going on. So first things first, I don't know where this tungsten's been. So I'm gonna swap it out. So I don't know where it's been. Another one is, what do you see here? What's going on with this tungsten?
They sharpen both sides.
They sharpen both sides. All right, so we don't know what tungsten this is. We don't know. Now we can assume, oh yeah, it's the blue ones, the 2% lanthanated, because that's what we got in the shop. But I have a whole bunch of different colored ones here. And now, depending on the shop you're in, you know, this could be who knows what. You don't know what this is. So again, when you're working with them, only sharpen one end, okay? Very important, because once it's sharpened on both ends, again, it becomes mystery metal. I don't know what this is. I assume it's tungsten. I don't know what type of tungsten it is. Now it becomes junk. And remember, these things can be up to $10 a piece. So we want to make sure only sharpen one side. Another one is, tungsten is also incredibly hard and sharp. So if you sharpen both ends and you're carrying it, you bump into somebody, yeah, bad news. So only sharpen one end, because with both ends sharpened, boom, this will go right through anything and you. So be very mindful of that. This is highly dangerous. Very, very, very dangerous. So you want to be very careful of that. So I've got some fresh ones I sharpened up. So I'm going to use a 2% lanthanated because that works fine. Here we go, right there. This is a 30 degree angle tip, which is a good all around size. Now, why do we choose different angles? The main reason is because it controls depth of penetration, all right, and it controls the size of our weld pool. So I've got two here. I've got a 30 degree and I've got a 20 degree. So you can see this one is much, much pointier than this one. So what it's going to do, I should have a piece of chalk here if I don't. Oh no. Well, what it's going to do is this. If you have a really blunt point like that, okay, A really blunt point is going to give you very, very, very deep penetration with your tungsten. Say 45 degrees, you know, really blunt. You're gonna have very, very deep penetration into the metal. You're also gonna have a really big weld pool. It's gonna be really like kind of big and hard to control a little bit. If I use a super sharp one like this at 20 degrees, contrary to what you think, you're actually gonna have a very shallow penetration. Less penetration, but a pinpoint, you know, really focused, tiny weld pool. So if you're welding really thick material, remember with TIG welding, you generally 1/4 of an inch is really pretty much the maximum you want to go with TIG welding. If I'm doing 1/4 inch material, I have a really blunt cone. So I ensure I got super deep penetration and really get in there. If I'm welding sheet metal, really thin stuff, I mean, something like this even. I just thin stuff like that, or even really thinner. I want to use like, you know, 20 degrees, maybe even 15 degrees, a needle. I'll have very little penetration, but I'll have lots of control. So you can use the shape of your grind to control that. You know, if you're like, ooh, I'm penetrating too deep, well, sharpen your tungsten up. It'll pull the weld pool back a little bit. If you're like, well, I need more penetration, blunt it up. You know, 45, 60, you'll get that penetration at the expense of some control. So I'm gonna use, I'll probably take this one to 30 degree because this is a little bit on the thick side here. And one good thing is when you're working professionally, I always keep a full box all sharpened and ready to go. So you have to think time-wise. If you've only got one sharpen, you have to get up and sharpen it every few minutes. How much time are you wasting? All right, so what you want to do is have, you know, I've actually got 3 boxes of these with me here. Have a box. No, they're not. They're not.
It's like 130 bucks in there.
Yes, they are expensive. But in terms of time-wise, when you're working at the bench, if I've got a whole bunch of ones here ready to go, I can just swap out and keep going, and at lunchtime or break time going, I can sharpen up all 10, come back, and I'm ready to go. It saves time and doesn't interrupt your work process. Or you're asking about order of operations. You don't want to interrupt your flow. Once you get into that groove, you don't want to continually break it up, because once you get, okay, I'm really there, you don't want to have to get up, walk across the shop, come back because you've lost it. Now you're like, where was I? So keep your material prepped and ready to go so that you don't have to break up that thought process. It's a really important thing. So I'm going to load up in here. And again, some people even wipe this down with acetone. I just sharpened it so I know it's fresh. And I know where it's been, so it's not going to be dirty. Stick out. Does anybody know how far can you stick out the tungsten? Does anybody know? How many? Diameter of the tungsten. Here's the rule. If you have a ceramic cup like this, your maximum stick out can be 3 diameters of your tungsten, which is going to be about there. If you have what's called a gas lens, I'll bring one into my other kit, but it's at home right now. A gas lens is, you've probably seen them online, it's that mesh, the cup with the mesh inside, yeah.
Usually a glass cup.
Yeah, so what that does, the gas lens is going to cause the gases to flow very straight. So instead of being like a cloud coming out and going everywhere, it flows out kind of like a stream. So you can actually extend it 6 times, much longer. So that's one of the advantages. Why do they want to use a gas lens versus just using ordinary ceramic cup? Because you get greater stick out. Really important when you're doing small stuff or little corners, it makes a big difference. So you got about 3. You can go a little more, it's gonna be okay, but generally that's kind of your stick out. And the easy way to tell if you have too little stick out is this. If you notice your tungsten going blue, when you finish welding, you're looking at, why is my tungsten blue? That means air is getting in there. That means you have too much stick out. So if you're welding and you don't get that, you're fine. But if you notice it turning blue when it cools, it means you got too much stick out. So now you got to pull it back. The things to watch out for is your welding. Get your proper setup when you're welding, very, very important. So we're ready to go. It looks pretty good. How to hold it. I like to wrap this around my arm like this. So this way, I don't have the cable dragging on my wrist and I have really good control and movement. Some people like to hold up here, hold back here. It's really up to you how you hold it. There's no right or wrong way. Just be comfortable and make sure you have good access to everything. Now, gas-wise, for welding, you really want to make sure your gas is set between 25 and 30 cubic feet per hour. So if you have too little, it's really going to affect your weld in a bad way. You're going to get a lot of air contamination, and you're going to see around the weld, you'll see like brown and black staining in the root. You don't have enough gas coming out. So check and make sure you do. Give your pedal, turn on your power, give your pedal a hit, and let's see what we got. Oh, this way. There we go, and here we go. All right, let's see what we have.
The gas ain't on, I don't think.
Yeah, it should be on. It should be on. All right. All right, we're good. About 30, that should be fine. So this is an inverter style machine. So as you notice, it doesn't make any sound. So inverters are nice because they're really small, they're very light, really good machines. They don't make any noise whatsoever, which is really good. The transformer machines will be the really, really big ones. So if you're in a shop, how do you tell the difference? Transformer machines will be immense. They can be things like the size of like a washing machine that weigh like 1,000 pounds. The great thing with inverters is that now you have the control over a couple of parameters which you don't have with transformer machines. One is you can control your waveform, you control your frequencies. That's one of the things I wanted to look at today because it can really make a huge difference when you're welding aluminum. Huge, and a lot of people don't go into that. And I want to kind of touch on that this morning to help you guys out because it can also help with steel as well. So if we're looking at the controls, I'm going to set this to AC first, and at 130 amps. So how do we tell how much amperage we need? How do we tell? Thickness of our material, exactly. So this little thing right here, let's see what we got. I mean, visually, this looks like a 1/4 of an inch. Let's just check to be sure. So a 1/4 of an inch will mean how many amps do we need? Yep. Yeah, about 250 amps ballpark. It's a starting point. Doesn't mean you need to, but you can. Let's say you don't have 250 amps. What could you do? Huh?
Heat it up, different gas.
Two good suggestions. Yeah, you could use either a different gas or you could preheat. So a lot of times preheat anyway is a really nice thing to do. If you have the ability to preheat the aluminum, by all means, do it. Okay, it'll really save you a lot of agony. If the material is warmed up, it's going to weld a whole lot better. Think of it like preheating your car's engine in the wintertime. You know, race car, they do that for racing. They actually preheat the crankcase and engine oil before they put it into the race car. So that way the car is already warmed up to operating temperature before they even start the race. Think of it the same way. So if you have the option, do it. It'll help you out a lot. Another one is gas. So we're using argon, but you can use an argon helium blend or straight helium. I don't know if you saw the videos I posted of someone welding aluminum with DC. The trick is you have to use pure helium. The reason why it's not used so much is because helium is just mind-blowingly expensive. Though helium does have absolutely incredible welding power. If you have the option to try it out sometime, I highly recommend it.
It's for better penetration.
Yes, it gives insane, not better, insane penetration.
Insane penetration.
Insane penetration. And
It's usually a mix with.
well, it can be straight or it can be an argon helium blend. It can be either one.
You can use straight.
Yeah, you could. So the helium has what's called greater thermal capacity. It can carry more energy. So the plasma is a lot hotter. It's the equivalent of taking like an ordinary engine, adding like a turbocharger with nitrous onto it. So it's much hotter than you're normally going to see. Much hotter, deep penetration. Downside is you sacrifice control. It's much more like zzz, much more skittish, hard to control. But if you don't have the power and you got to weld something thick, get a bottle of it. So that's an option there. If you're in a pinch, that's a great option to do. I have some at home, a blend, and the cost was like, oh, yeah. I save it for emergencies. Yeah, but it was very expensive. Okay, so we have our frequency right now. We're doing 130 amps. I'm going to boost it. I'm going to max out at 210 amps. That should be fine for our purposes here. I got high impulse, and you have the option here of doing some things with your frequency. Like here you have pulses per second. And you can do some things with frequency here, which can do some very interesting things. So here we go. So pulses per second. So here are your parameters. Pulses per second is going to be. So have any of you tried using that for welding, using pulsing?
I did 37 days.
Yeah. So pulsing it. Do you remember we did some of that with the MIG welder, using your finger to manually pulse it? Remember, it gives you a little bit more control. So with TIG, the same thing. If you're welding super thin materials or out of position, it'll just basically be like boom, boom, boom. You can pulse it like 1 per second all the way up to some cases, depending on the welder, it could be like several hundred times per second. That's one parameter. Now another one is frequency. So with AC, you're going to hear that very distinctive bzzz, because your frequency is moving back and forth. Your power is alternating. So what's happening is the current going one way into the metal is heating it up. Okay? Now the return going this way, what it's doing is it's going to be blasting impurities off the surface. If you're welding, you'll notice it turning white. You'll notice this white like speckle happening. That's the return pulse going this way. That's blasting more aluminum oxide off the surface. That's got to be removed. So that's what that pulse is doing. Half the pulse is heating the metal, half the pulse is driving that aluminum oxide and contaminants off the surface. Now, we can control that with an inverter. You can, normally AC is like this. It's half one way, half the other. With an inverter, you can start to play with that thing. It can be 30-70 or 70-30. You can change that, and by doing that, you can kind of tune how it behaves, and it can make your life a lot easier. If you're welding just straight 60 hertz, which is 60 times per second ordinary like current like this, you don't get the same what's called cleaning action, which is removing the oxides off the surface. So what are we looking for? You want to have a good weld bead, and you want to have a really small track of cleaning along the sides. Like, you don't want it huge. A nice, neat, right in the toes, little nice clean track of that white cleaning action, they call it. You want it to be as small as you can get it, just beyond the size of the weld, because remember, it kind of messes up the surface a little bit. We do that by adjusting what's called the cleaning action. Okay, and that function in here is, let's see, you have here AC wave shape. See the balance over here? It's called balance, AC balance. That's going to be that function, okay? 70% means it's going to be 30% clean, 30% cleaning action, and then 70% your regular like, you know, heating pulse. 30% is a good starting point. You know, 30% works really well. You can go up and down from that point. So that's a good starting point. About 30%, 33% around there. You know, I'll leave it at 70%. The next one is your frequency. Right now it's 120 hertz. I'll set this to 60. That's going to be ordinary old style aluminum welding. Like, it's the same frequency as power going through our lights. 60, right? 60 times per second. So let's hear the difference and let's see what it looks like. So I make my gloves right here. Remember, you want to use dedicated TIG gloves that are not used for anything else. If these get rust on them, they get oil, whatever, you're gonna have problems. So if you're doing a shop where you've got stainless, you've got mild steel, you might want to have gloves dedicated for just one of those things, you know? These gloves only touch aluminum. These ones only touch stainless. They don't touch anything else. Okie dokie. So I'm curious to see how this is gonna come out on the video.
I got something on too.
All right, very good. All right, so I'm gonna get my pedal comfortable. So one of the biggest things for TIG welding is we want to be comfortable. So it's very important to have a chair that's the right height. If you need to put like a pad on chair, whatever, do it. Get the foot pedal placed where it's comfortable. You can move your foot easily, you know, and it's not going to fatigue you. So spend the time doing that before you start welding. Don't just dive in, but get organized so everything feels good for you. So the first thing I'm going to do is, since this is a high frequency welder, I want to get my puddle started. Now the two types of welders we have in the room are high frequency start and they're called touch start. Touch start, as you've used, you got touch surface and called lift off. High frequency, there's an invisible high frequency pulse that's going to go from the tungsten to the metal.
Basically, you don't have to strike it.
Yes. So once the machine senses that, oh yeah, it's there, it's going to send through the high power charge right after it. Think of it like how they make a bridge. You throw a stone with a little thread across the canyon. That allows you to pull the heavier cable along behind it. That's what this is doing. Same thing. So the little thread, and sometimes you can see it. You'll see a faint purple thread going through the air.
You can see it before it strikes?
Yes.
I've never seen it.
Sometimes you can see a little faint purple like squiggle in the air if things are just right. That's a high frequency pulse.
You can see it against your glove sometimes.
Yeah, the same thing is true of lightning. Sometimes you can see that flicker in the air.
Yeah.
Boom. What you're seeing is a high frequency pulse actually hitting the ground and the charge following behind it. The same thing's happening here. All right, so what I'm gonna do is I'm gonna form my puddle. And when you form it, you wanna hit and then move it in like a little circles a little bit. You wanna form the puddle and stir it. You wanna get stirring. What you're looking for here is, because aluminum does not glow, I want to look for shimmer. I want to see the puddle shimmer a little bit. I know it's liquid. Then I'm going to start adding and moving my puddle along. Okay, I'll make sure here's the side that's not stamped. All right, here we go. Cover up everybody. So right now you can see the shimmer action. So right there, take a look. So that light right here, that's the cleaning action. So that is the aluminum oxide being blasted off the surface before it's melted. So you can see it right there. So it's not melted yet. So that's the cleaning action. So I'm gonna keep going and get this liquefied. You can hear by the sound, it's kind of like, it doesn't sound very, very energetic. So that's 60 hertz. Let's see if it works. We're going to shimmer now. so that's on 60 hertz. And you can see the white is a fairly substantial area of cleaning around the weld. But you see the weld itself is nice and clean. There's no black speckles on there at all. It's very smooth, and there's no gunk on there. And that's all due to cleaning. That's really the thing here. That's really just paying attention to cleaning all your material out. That's really the secret to aluminum, is just being clean and being conscientious of that. Because I know when you're working, it was like, there's black stuff everywhere. That's just the dirt that's there. It's invisible to us, but it shows up when it starts to burn. So that's 60 hertz. Let's pump it to 120, and let's see what it sounds like. So I'm gonna go back over here, and I'm gonna adjust my frequency back up to 120. Here, some machines can go up to 400. And just as a brief aside, I'll bring my TIG welder in one of these days coming up. I personally like machines where you've got knobs you can see. Like my machine has like 12 knobs on the front. It seems like a lot, but the advantage there is I can look over at a glance and I can see where all my parameters are in one glance. And I can just reach and fiddle a knob just like that. Here, if I have to punch through menus, for me it breaks my concentration, because I'm like, oh, where's that menu? It's not intuitive.
My boss is a P&H. Have you ever heard of those?
No.
It's huge. It's a huge yellow TIG welder. It's from the early 50s, and it has a high frequency start on it.
Yes.
I didn't know they had that back then.
Yes, so what we have there is a transformer based welder. Or a transformer is the same thing as, like, the little wall wart you use for charging your phone or anything else, the little box, but just multiply that by about 1,000,000 times. That's really what it is. Now, so the machine does have high frequency start, but back then, the high frequency was generated by a high frequency generator, which was what they call a set of points. What they do is they're running the current between these, almost like a giant spark plugs, that generates that spark. It's actually really, really, really terrifying.
Yeah.
If you can pop the hood, and there should be a panel on there for adjusting it. If you can pop the hood and take a look, it's worth checking out. It'll blow your mind. It's like a giant purple spark. Like, the points are like this big and the spark is like that. It's really scary. Oh yeah, that's exactly.
I'm using
very cool. Yeah, very nice. Yeah. So somewhere on there should be the point adjustment, the panel for accessing the points to adjust them. Oh yeah, I've used machines like that.
Yeah, it's really cool.
Yeah, very nice. Now the advantage of that is this: the transformer machines are very much old school, like old school cars. There's nothing electronic in them. They're all wires and switches and stuff like that. They'll last 1,000,000 years. Downside is they are extremely heavy. They're power hungry like you wouldn't believe. They're very inefficient, but a machine like this is light, you can carry it anywhere, very efficient on power, very powerful. Downside is it's a computer. If if I drop this off the table, there's a good chance I've broken the circuit board. A big machine like that, you can drop off the back of a truck and it'll never die.
Yeah, this thing's so cool.
So there are certain things you have to be aware of. I've worked at a shop where we killed one of these things. We were welding stainless steel, welding at 250 amps, 8 hours without stopping. We blew up the heat sink. I mean, we welded hard. I mean, flat out, 1/4 inch thick stainless steel, 8 or 10 hours without stopping.
My boss's rig just caught
Boom.
fire. He had the truck with the flatbed and the big beacon on the back, the whole thing caught.
Those are cool.
Burned to ashes.
Oh no. So let's see what 120 sounds like. So listen to the sound, okay? And let's see if the behavior is any different. All right, let's see what it sounds like, see what we got going on here. And here we go. So I'm gonna start above the surface, get my puddle going. There we go. So a little bit, see, it's a little bit smaller. I've got a little smaller puddle in there. A little different. I'm gonna dial back on the cleaning action to 70. Now, just so you know, depending on the maker, okay, and this is a weird thing, when they call AC balance, like if I look on here, here it shows 70%. Out here, it's not standardized. Some makers, when they call 70%, they mean 70% cleaning action. Other makers, it's 70% heating. It's not standardized. I don't know why. So you have to actually look. In this case, the thing is so wide that this has got to be the wrong way. So I'm going to set this to 30, and let's see what it looks like, because it's just bonkers. It actually won't let me go down below 50. I don't know why. Let's try 50%. Another common myth is this. You may have heard people say for tungsten you got for aluminum you have to ball your tungsten.
Yeah, I heard that.
You don't need to do it.
I don't.
Yeah, you don't. Now, you did, if you're using a transformer-based machine, and I think I've got one here I can show you. If you're using an old-style transformer-based machine, you had to do something like this.
Is that green?
No, this is lanthanated. You had to ball it like that. So you had to actually preheat it and kind of melt the tip into a ball to deal with the excessive heating. That's what it was used for.
So the arc's not as direct.
It's not as controlled as a transformer is. With a transformer-based machine, with an inverter-based machine, excuse me, you don't have to bother balling the tungsten, which means you have a nice, tight, controllable arc, which is great. It's much better, much better. So let's see what we got going on here. We'll do it again, and let's see what we got. Okay. So cover, put over here. You can see right there, I must have missed something on the edge of the plate. You can see right there very distinctly what they call that salt and pepper stuff. So you can see right there, that must be the edge where I didn't actually clean it off, and you can see the dirt. So if you get that, what can you do? You gotta grind it out. So if you do get that, don't even think of a welding over it. You're gonna have to physically remove it, clean with acetone, and then go back into it.
Stainless brush as well.
Yes, with a stainless brush, yeah. So you can actually grind that out if you do get that kind of contamination.
And you can't use a regular brush because it will dig into it.
Yes. Now, interesting thing is, look what happened when I put on that 50% balance. So you can see what happens there is there's too much heat coming through here back into the tungsten, and it killed it. So I'm going to load another one and we'll go back to 70. Yeah, it welds a little different from mine.
That's sharpening.
Oh, it's okay. That's why I have a whole bunch. That's kind of why I like the machine I have. All machines are going to weld a little differently. I really like the way my AHP welds. It works for me, you know. So this one is a little different. Mine has a much tighter cleaning action around the weld than this one does. So let's run some more and see where we are. Get that out of the way, get the wipe down. I'm gonna go over here because I know that's clean and away from the dirt and grime. haven't done this in weeks. See, it's a little better. It's a little tighter. It's a little, the clean action a little better in there. One thing that if you notice when you weld, you want to trail off. You want to, don't stop abruptly. Kind of like gradually practice on trailing off on your power and then turn off. When you do that, go back over your weld, okay? It's very, very important whether you're doing aluminum, stainless, or steel. Trail off and then trail off over the surface of the weld backwards. What that does is it's going to prevent you from getting a big crater crack, which is a big issue with aluminum. And it also, it'll prevent also getting like a crack through the center of the metal because you're trailing off the heat over the weld. So it's a very important thing that you want to do when you're welding aluminum. If you don't, you'll get a weird kind of thing going on there. Another one is you want to practice going like this. You'll heat your puddle and then back off a little bit as you're adding in. Don't just run it across because you end up getting, it balls up really bad. So go back and forth kind of like this. Kind of come in and dip in as you go at the edge of your puddle as you go. It'll work a little bit, it'll be a little easier to get in there. Cover up. A little uncomfortable, here. But those are coming out pretty good, you know? Those are coming out pretty good. Let's boost the frequency and see what it does. So I'm gonna go even higher. And let's see where we go. Post flow, frequency. There, let's go 200. Okay. So why would we change frequency? This is really useful when you're welding super, super thin material. The high frequency is really good for welding like really thin aluminum where you have a real chance of burn through, and you don't want to do that. High frequency will allow you to get a little more control with super thin materials. This is a little on the thick side actually. I actually have the pedal floored. So part of the difficulty with welding here is I have no modulation control. I have to pedal all the way down for something this thick. You need a lot of power for AC, you really do. You need essentially like twice as much power as you do, say, if this were steel. Because remember, your pulse is going two ways. So it's very power hungry, and you really gotta make sure you have enough capacity to weld it. So let's see what 200 sounds like. Hold up. It's comfortable here. Ooh, I like that. That was nice. Wow. Yeah, 200, very tight, really controllable. That was cool. So your frequency was the menu over here, all the way on the right. You'll see the button marks an AC waveform. So that one, AC frequency, that's that control, you know? So that can really help you in certain applications. It's kind of fun. So let's see about you running a T or something. Ooh, these are wet. What is on here? Gross. Quickly wipe it down. Oh, very important. If you're wiping acetone, don't use your TIG gloves, folks, because you get these soaked full of acetone. Bad news. So, yes, you will catch on fire. So we want to be really careful about that. It could be kind of horrendous. So let's be careful out there, everybody. So there are ways to stick weld aluminum. I'm gonna see if I can get some rods because it's very cool and weird. Huh? Yeah, it's kind of curious because I've never done it, and I posted some videos on that if you got a chance to see them. They're an announcement, so take a look. It's very cool, and it looks like something that'd be kind of fun to explore. Now, the welds are honestly horrendous. They're like really, really ugly. But it's one of those things like if you positively have to do it, you can. So I think it'd be kind of cool to check that out one of these days, just to see what it feels like, because it's probably very strange. It does not weld like normal welding. So I'm gonna tack these on and run a bead. I haven't done this in a while, so I think it's good practice. Cover. The second material is usually square, the cover. There you go. All right. Okie dokie. So when you're welding in corners, one thing you want to do is when you're welding in a corner, pay close attention to your nozzle and your tungsten. This is one of the things like, why are there different size ceramic nozzles? Why are they around? Big one is they allow you to get into corners. So what you want to do is check and see how you fit in there. Like if you're using, remember you got 3 diameters of Stickout on your tungsten, does it allow you to get in close enough and still get good gas coverage? So if you got a really tight space, switch your nozzle, get a smaller nozzle.
Also, look at the mesh. You use a wider cup, you can stick it out more.
Exactly. So if you've got something where you've got like, I can't get in there, what am I going to do? A gas lens could solve that problem by allowing you greater stick out to get into a smaller space. So keep that in mind, okay? These are all things that could really make your life a lot easier. I'm going to give this just a quick brush over before I begin, just to kind of help things along here. Again, nothing comes off, but that's because you can't see it, but it is there. All right. I really wish there is no larger wire. Oh, I honestly wish I had larger wire. That's one of the issues I've had. That's one of the tricks with welding on you. You can see this is what happens. If your wire is if this happens to you consistently, you're balling up like that, this means that your wire is probably too small. So this, I really should have wire that's probably 1/8 of an inch thick.
Yeah.
Yes, it is. Ooh, sexy, thank you. Very nice. All right, so this is thicker. Hopefully this will help the problem. So again, like we were talking earlier, if you find you're having trouble with your puddle being too hot and you can't control it, go up to a larger diameter wire. So long as the wire isn't thicker than what you're welding, you can use a thicker wire. Like this, look at that, it's half the thickness. This should be ideal. So I'm gonna run through here. Let's see what we got going on here. I'll try and weld this way so you kind of see. I'll try and go sideways. Let me see if I can do it. So what I want to do here, the trick here is I want to get my puddle bridging between the two sides and then carry it forward without melting through. A little tricky on aluminum. Now, another good thing is, if you have a long seam like this, it can be a good idea to put a tack weld here and here before you begin, because you may end up breaking a little tack like this off. So sometimes that can be good insurance to do. Weld here, weld there, then now you know this isn't going to move on you. So let's see if we can do that. Cover. Yeah, it's struggling. Yeah, it's
With
even.
that thickness, it's struggling?
Yes, yes. You need a lot of power to do aluminum. A lot. An enormous amount of power. So even though this is 210 amps, it's having. See, it's like I was like really like. "Argh!" It wasn't bridging across the gap. So I'm sure as you've noticed when you're TIG welding and you're bridging a fillet weld, how do you know you've got the right amount of power? When you get in there and you hit it, you want to hit it very fast and hard. Your weld pool should go boom right across both sides immediately. If you have to sit there monkeying around with it, like, oh, it won't go on both sides, you don't have enough power. So you should go in there and just go boom, and it goes across both, and then you can just carry it right across very, very quickly. In this case, I'm just like, come on, come on, come on, come on, come on, come on, come on. It doesn't want to go on me. So it's giving me a really, really hard time. So I'm gonna drop my frequency a little bit, back down to 120. I think that will broaden my putt a little bit, and let's see what happens. I'm gonna continue, and hopefully I can get it across this time. But it's very hard. So if I were welding something like this all the time, I'd need a much more powerful machine, a lot more juice to do this effectively and not like make a mess of it. Here we go. You notice at the end it's sped up a lot because the middle started to get hot, and I can say, oh, now it's flowing. Ooh. Beginning, it was really not happy because it was cold. That's why if you have the opportunity to preheat something, it can really help out a ton. Right about here, I felt it really start to flow. I was like, yeah, here we go. So you can see on the weld itself, you know, you've got nice, pretty good color on there. There's a little bit of yuck on there. I don't know what from. But, you know, nice, good, smooth color. You don't have any salt and pepper on there or anything. There's no burn through. You see on the other side, there's no burn through or anything. So it came out pretty good. You know, it came out pretty good. So one of the big things there is, if you have trouble, like in the beginning here where it's not well, you can tell it's cold and it's not heated up, you can actually take the torch, pass the torch, and just run it back and forth until it heats up, then weld. So just come across and just go back and forth a bit until it gets nice and hot, then go into it, and you should be okay. So I'm gonna weld the other side. It should be nice and fast now because it's already been heated. Let's see how it goes. Cover up. Comfortable. There we go. And yeah, it looks fairly good. Again, this welder's a little weird. I like mine. It's like driving a car. I like driving my car. This one feels a little different than my welder, so it's a little different. But that's just kind of, basic, simple aluminum weld. I mean, the really most important thing here is that it's clean. That's really the most important thing here. If you follow the clean protocols and you just, clean, Scotch-Brite, if I have more of this, I can give you Scotch-Brite off, clean again. That should erase away probably 90% of your problems with aluminum. That's really the thing. And you should be fine. Yeah, and everything should be all right. And you can feel, if you had gloves, feel how hot this thing is. This is smoking. Yeah, this is smoking right now. This is one of the reasons why I say, well, when do you use a water-cooled torch? Generally, the rule is 250 amps is kind of your borderline there. Below 250 amps or so, you're okay. But once you cross that border, you really run the risk of incinerating your torch. So right now, would I do this for a long time? Probably not. This is really, really, really like, wow, almost uncomfortable. But you see, that's the kind of power you need for aluminum. It's very, very power intensive. If this were steel, this would be no joke. You'd be like, yeah, no problem, man. Aluminum, ouch. It's a whole different thing. So, stainless. So I got a couple of things here. Just quick stuff on preparation, just quick things on preparation. So let's say you're welding something like this, okay? Very important thing with preparation of stainless is that you remove any burrs that are on there. So like if you're welding to the plate, you want to make sure that your stainless, you're removing all the burrs on the surface, like in the edge, like sharp stuff. Remove all those, because those can have a negative impact on your TIG welding. And give it a good brush off. Use this side right here. And you can see, look at the difference in the color. See, stainless will have kind of a yellowish color to it. When you brush the oxide off the surface, it gets much brighter. You can really tell. So you want to always prepare it the same way. You want to, like aluminum, clean your surface, brush it off, wipe it down with acetone, even do the interior. It's very important because when you're welding, all of that is going to get into your weld. It's going to melt from the inside, come onto the outside, and get all over the place. So you want to be very careful about those things. You want to make sure that you do clean those things, and you clean off your surface. And I don't know what this stuff is here, but I'm going to use a wipe down right here. Nice and shiny, nice and clean. Okay, so I'm going to leave this, I'm going to go over it, change my frequency over here, polarity. The frequency, I'm going to change over to DC current, 120 amps, sounds wonderful. The pulsar, pulse per second. Yeah, what is that? So let's see what 1 pulse per second sounds like. Okay, this is so useful when you're working. It's really nice to have for control. It's very cool. So let's see what it sounds like, pulsing. Okay, pop it up. You hear it? Yeah. Huh?
How many pulses?
That's 1 per second. It doesn't do anything.
Yeah.
So let's boost it. Now, one thing to keep in mind is the pulsing it's almost like a strobe effect, so it can be kind of irritating. You might find pulses that are like, I can't stare at this. Let's see, I want to do about 10. Let's try that. That's 12. Let's do 12. And I'm going to switch out my tungsten again because this one is contaminated with aluminum.
Sure, you're falling off during class, man.
Sorry, boss.
No, it's all right. You never know. I mean, I got mine on. Sometimes you got family things happen. I got 3 kids at home, so you never know. You know, you never know what's going on. All right, so here's pulse, and so now this is 12 per second. So let's see what it sounds like. And trail off at the end. Nice and easy.
That sounds sick.
Why does it seem like your high frequency starts?
I'm not sure.
There's a pre-flow.
It's not,
on that,
right?
Huh?
There's a pre-flow on that.
Yeah,
That's why it's delayed. The pre-flow.
Yeah, that's not high
Pre-flow is
frequency.
fine, post-flow is auto. High frequency pulse is on. It's all on. It could be the ground
Before
could
I
be
saw it,
something.
it said pre-flow. It was the time down, and then it hit it.
Oh, so let's put that to 0. Well, what does it do? All right, what pre-flow does is it's going to pump argon through here first to give you a shield before you strike the arc. So that's why pre-flow and post-flow are really nice controls on better quality TIG welders. Usually that post-flow, you know, it cools the puddle after you're done. Pre-flow makes sure that you're not pumping oxygen into the weld when you start. So we'll put that back up a little bit. Let's give it like 1 second. And then when we have half a second here. And I think that will do well. So you see the weld is very small. Look at that, really tiny. You see? Very tiny, very easy to control. What it does is it allows the tool to freeze for a fraction of a second before you add the one again. So if you have really thin materials, it allows it to set up before you continue adding your next pulse in there. So if I turn it off completely, pulser, now it's off. And again, the pulser with inverters, you have yet another parameter you can control. Your waveform again looks like this, right? Like that. With an inverter, you can control what they call your background. You can control upslope. You can control your peak pulse dwell time, how long it stays up there, and when it comes down. You control all of these areas independently.
That's so much.
So you can control the entire waveform, custom tune it to exactly what you want it to do. These are very advanced functions. But they're worth, as you get better at TIG welding, there are things you can control, especially on really thin materials. This can make or break the whole thing. So as we go forward, it's something you might want to like start reading about. Look online, I'll see if I can find information about that. And see what it does, because it's really, these are advanced things a lot of TIG welders do not understand. They don't know, but they can really help you out. You don't have to, it's not just one size fits all here. You want to really see what's out there because it can really help you. If you can do the job no one else can do, hey, that makes you really good. That's you keeping the job when other guys get laid off, you know? So I would kind of aim for that. I am welding with stainless on here, but I guess it doesn't matter. All right, let's see what we got. So this is without the pulser. We'll see how different it is. So I'm not pulsing with my foot. I'm just drop by drop walking along. There we go. So you can see the pulse weld is actually colder. At the same amperage, it's a little colder, it's a little higher, it's a little stiffer. So on thin materials, that can be a big advantage. In fact, when I welded the dodecahedron and the cube, just for a hint, I pulsed those. I used a pulser so I could weld 16th inch steel without burning through. That was the secret. It's really, really nice. So if you want to try welding some of the thin material trying the pulser and trying different settings, check it out because it really makes a huge difference. And so many welders I know, they're like, I've never pressed that button in my life. It's like, well, maybe you should. You know, it's like the control in the car you never use. I never even knew it could do that. It's like, didn't you ever look? Like, read the manual, dude. You know? So that's without the pulse. And again, you can do this with your foot. So if I'm using my foot, of course, what I want to do is I'm going to pull going, and now I'm pulsing with my foot. Then I pull going, pulse, lay off my power, pulse, lay off my power. You know, you can do it manually. You don't have to have some fancy setting to do it. And it gives you the ability to control your puddle. So you can use both of these things. It's really easy. So let's try welding this to the surface. Let's see what it does. Just for fun. All right. Now I'd really love to fusion weld this to the surface, so I can't tack weld it that way. So let's see if I can. I'm gonna extend out my tip a little bit. So I can get in there. All right, let's see what we can do. Cover it. Oh, there we go. Perfect. There you go. So that's like the best way to tack weld stuff together. So that's a fusion tack. Yeah, fusion tack across the surface like that. So you'll see it all of a sudden go poof, right across both, let off your power, and you're done. So you look for that where it suddenly goes boom across both of them. And what you want to do is you want to weld it hot and fast, and you can tack weld stuff together very, very quickly, like that. So that way now I can position it any way I want to go, and it's not going to fall apart. And it makes my life so much easier. So if I were welding this, like for real, how did you weld that? Flat like that? It's like, if you have the option, you know, why not like, you know, I do this. I'll do something like that. Tilt it. So that way you're welding in a more optimal position. Okay. This way, gravity is my friend.
And you just did 4 opposite corners, correct?
Yeah. So this way I'm using gravity to pull the metal down into the weld rather than fighting it. So if you have the option to tilt your material in some way that will make, like, you know, your life easier, it's like, by all means, you know, do it.
Oh, crapple.
Dropping the stainless rod.
This one else is stainless.
Okay, thank you.
Oh, right.
Oh, you have it? Thank you. So tilting allows me to get in there, not have to stress out. I can relax and kind of take it easy when I'm welding.
I love that smell.
Now, if I have positioner, I can do the rest. I'll finish these other ones flat. You hear that pain? That's so weird. Is that the aluminum? Is that this or this? What's making that sound? This? Really?
Something inside.
Oh, awesome! Awesome! Check it out. Wrong wire. Check it out. Look what it's doing. Yes, isn't that incredible? There you go. That's why you gotta use the right kind of wire. You can see it right now. Look at it cracking.
You can hear it.
Yes. Yes, exactly. So that is a real world confirmation why you want to use the right alloy for this and why 316 is not the alloy you want to be using. Look at that. So, yeah, this is 308. So you need to use 309 because 309 has the correct chemistry to blend between.
Did mine crack?
No, it didn't. So that's good. So yeah, I mean, 316 works. It's really just about the corrosion thing. But this is a really good demonstration of why just a slight difference in the wire causes some crazy problems.
Could it be the heat? Because I did mine lay wire and I just kind of just weaved it together. I didn't like do the dab and all that.
No, it's very much, no, this is just chemistry. This is the metal chemistry. So that's pretty cool. So you can see that with the 308, even though, yeah, 308 would be perfectly appropriate for this, 304, it can't join between mild steel and stainless successfully because they shrink differently. One shrinks more than the other. Stainless shrinks much more than steel does. It has what they call half the thermal capacity. So it takes twice as much heat to heat up stainless, but twice as long to cool down. It's slower, let's say. So what happens is this steel shrinks much faster than this one does, and that's why it breaks off. So you can see on there, that's pretty cool. It broke right off. Yeah, I don't think I have any 308. I think I just have, 309. I think I just have 308, unfortunately. Yeah, I think this is all 308 wire. 309 is generally kind of repair. You know, people use it when they need to. They don't really carry it around. Well, you know, this is a pretty nifty demonstration right there. That's pretty cool. I like that. So just some quick stuff with TIG welding that I thought you'll try out, see how it comes out on you. There are some pieces we cleaned up right there. So if you want to come in and use it, be my guest. And I guess we were working on some other things earlier in the day, so if you want to get back to that, you're welcome to. Now, coming up, make sure that you don't owe me anything in Blackboard. So look through, make sure you have no spaces in your homework. Some of you owe me stuff. Okay? So look in Blackboard. If you owe something, get it done. We have a final coming up. All right? That's next week. Well, so last week, well, you have one with Keith this week, right? Yeah. But yeah, I'll have something filed for you. We'll do a print for the final, and because we're doing like you know, we're kind of sharing a lot of the welding stuff, so I'm focusing on prints. So we'll do a print for the final, and you know, we're still doing a lot of the lab work in here that counts for our stuff here. So again, if you haven't taken a stab at that angle, that T thing, let's jump in and do it, because it's a lot of fun. It'll qualify us for the flux core section of this course. So it's a T. So you want to use one piece of this, one piece of this. Arrange it like this. So arrange it like that. There's like this, like put a corner here, and just like that.
You got more of that, man?
I can get some more of this cut up. So arrange this in a T shape like this. You want to have
This.
You want to have this one back. Oh, you started on this. Remember, you started on this last week. Yeah.
You want this MIG, Jason?
Huh? Yeah, use MIG. Yeah, use MIG low.
How do you get them up?